I think it is already time to greet everybody on our webinar. In other times, we would drink a cup of tea before the seminar, but maybe next time. So today, our today's speaker is a guest from Taras Shevchenko National University in Kyiv, and he is a physicist, but also interested in meta science, Artem Chumachenko. So I guess
you
can start.
I can continue. Hello to everyone. Thank you for your attention, for your participation in this seminar, and special thanks for opportunity to share our results about the scientometrics and all the problems that we've been developing since 4 years now, in partnership with the ScienceWise, with Boyarsky he's now in Switzerland, and others also. I think I'm sorry for my English. Probably at some points I haven't practiced that much because of the quarantine and other things. So you're welcome to ask questions along the way, because it's a lot of information, and I think it would be better to focus on some details initially than to ask when we already passed these things later. So our title here is a dynamic and static structure of scientific concepts network and hot topic detection. We will, let me see how this works, because okay. So the aim of our research were initially to measure the degree of generality of scientific concepts provided by the ScienceWise system. It stands for Web-Based Interactive Semantic Environment. It's a very interesting system which allows for scientists to upload and record their keywords or some physical concepts in this system, and to provide some review of existing concepts, to say how general they are, what are connections between the concepts, and so on. So it was made to help to find some groups of related documents, scientists, to help in everybody's research. We will say how we manage the problem, or our proposal to manage the problem to detect basic or generic concepts based on their research, their previous research of ScienceWise group. Also, we will talk about the methods we develop for topic detection based on the measure that we use here. It's a really old measure in some sense. It's mentioned in a lot of papers, but to our knowledge, we are the first who apply this measure to find the exact distance between the words, between the concepts or keywords, if you say so. And we construct some network out of these concepts, and we develop some methods to find the structure of this network, and of course, the main and very interesting point on how to find the hot topics out of the dynamics of this measure. We will talk about this in this talk. So the main methods of our research, we use the Shannon entropy to measure the general popularity of the concepts. So to say how popular exact concept, exact words or keywords along the time, and to measure the amount of information it carries with it. These Shannon entropy and its dynamics actually will help us to detect the basic or generic concepts. We propose to use as a measure some symmetric distance, which based on the mutual information of two concepts. These measure we're taking because of the structure of the data that we have, and I think this measure takes all the all the good points out of this data structure. So it's, I think, it's good combination. We use similar to friend-of-friend algorithm that usually people use in astronomy to define some set of concepts and to say that this is a topic, because the definition of topic is really wide, and many people can say that this topic and this is not a topic. So the straight mathematical definition is a bit difficult to say. In different papers it's different, but we will say what we were using as a topic. We use also, familiar to everyone, maybe the graph analysis to analyze the hierarchical structure of the communities of concepts and also topics. And yeah, the outline, shortly we will discuss the structure of the data that we get from ScienceWise to understand why we use it. We will say about the data filtering, so detection of the basic or generic concepts. We will say how we extract the topics and how we build a network out of the mutual entropy distance. Also say something about several methods of hot topics detections in this network, and a little bit about the future possibilities, future research that we are planning to accomplish. To your attention, there is two papers basically that we are now will follow. It's a recent papers, 2020, where you can find all this information explained with details, yeah, and some references. So about the data they were using, we were working with nearly 16,000 of physical concepts and which were published in nearly 500,000 of scientific papers on high energy physics, published on Archive preprint server from 92 to 2018. Yeah. Why we choose, why this data is good? Because, for example, the preprint server's data is much better to define the hot topics, since a lot of people don't need to wait for a year or half a year until their paper will be published, and then such systems like ScienceWise will download it, parse it, and extract some keywords out of there. So in this sense, this preprint server will allow us to really detect some hot things for some time interval. Here, this is a reference to.
Sorry, you on the first slide now?
Oh, not yet. The outline and then data for.
So it's just me. I see the first slide only.
Yes, me too. On the first slide still.
Okay.
Slide
okay, I'm sorry because I don't know why it happens. Let me just try.
Now it's okay, I think. No.
Yeah.
Let me do it once again. Maybe there was some problem with the application. And now, which slide do you see?
Data for 1637 and 0.
Slide.
And you know, maybe, yeah, fifth slide. Maybe it would be bad if you share your content via desktop, but not directly.
Okay.
Okay. Okay.
Yes. Okay. Let me do it like this. Let me just not like that. Okay. So I think like this. Yes. That's good.
Yeah.
Yes.
Yeah, that's better.
Okay.
You make a full screen, and then I think it would work better.
Yeah. So I made a full screen, so everybody can see everything, right?
Not. Okay yeah. It's okay now.
Okay. So this is the next slide, and everything's fine, right?
Fine.
Okay. So what kind of data we were taking from ScienceWise? It's data about the term frequencies of certain keywords or concepts. You can see the example of this data here. we have the article ID. It's certain articles which were published in that time interval that I mentioned. The concept ID, we have some unique ID for each one. And the total TF, it's how many times a certain concept were mentioned in this particular article. There are possibility also to find these TFs for title, abstract, or full body of the article. But in this case, we are working with some homogeneous approach. We take the total amount of citations of particular concept in an article. We also use MySQL in Wolfram Mathematica for data modeling. It's allow us for filtering and useful queries of the data from our database. And what worth to mention, we have initially two types of concept which were pre-selected by ScienceWise. You can see it in the second column as basic. Yeah, it's a true or false. So certain concepts are basic, were set as basic by the scientists on ScienceWise web portal. They said that this particular concept is something which explains some general ideas in physics. For example, electric field gradient, it's also set as an example of a basic concept. It was made by a human, yeah, and it made some problems because of the experience of some particular scientist to say that electric field gradient is a basic concept is based on its field of research. And sometime, okay, if it's something in biology or some other fields, the electric field gradient, maybe it's not that basic concept. And you need some statistical methods to say that for a particular corpora of documents, you may select them as basic or not basic. And this problem first time was how to say opened, yeah, and proposed some ideas by the ScienceWise company. They say, okay, that if we have a basic concepts which nearly in all documents in a very wide frequency range, we need to exclude them somehow. Yeah. They did it with certain methods that we will explain a bit later, and find the possibility to extract these basic concepts. We propose additional refinement of their idea, how to use the dynamics of the Shannon entropy to improve the selection of these concepts. What we, before we go there, we need to explain what we use as for the Shannon entropy. So the structure of our data, as I explained, is the term frequencies of each concept. And if you take a particular concept and say that it would be mentioned at least once in some number of papers, you can count these papers and set them on a vertical scale here. Yeah, for example, it's 450 of articles which mentioned only once a certain concept. Then there would be less number of concepts which mentioned it twice, 3 times, 4 times, and so on and so on and so on. So we will have some empirical distribution of citation of particular concept. Then we are able to calculate the Shannon entropy out of this data. It's explained here. You have a formula for this, but it's only one way to do that. You can also say that, okay, let us fit this distribution with some continuous, or in this case, it's a discrete function, and calculate the Shannon entropy out of this fitted distribution. Of course, we will get different results if concepts are very popular or not, because for very popular concepts, you will find that on X scale, you have nearly all these places would be filled. Yeah, you can find as many times as it possible to find a concept cited in the papers. So until 200 or 300 times. Yeah, there would be, of course, 1 or 2 papers, but also there are, as I recall, that it's 600 times one concept were mentioned in one paper. Probably it's a huge paper, but okay. And if you calculate the entropies for empirical and for fitted distribution, you can calculate the difference of these entropies, and what actually were done by ScienceWise group, and they said that this is a good method to extract the basic concepts out of this. But the main problem that I will discuss here, I will switch to another slide. This is their results, which we reproduce here. But you can see that in their case, they said all these dots are the concepts, and if they close to this median, they can be considered as basic. These dark circles is the basic concepts which was set by hand on ScienceWise web portal, yeah, before. And they say, okay, we have a good method because nearly all of them, all these concepts which were set as basic, we have on the median here. And but the main problem here, from 16,000 of concepts, if you will take only distance from it like 001, yeah, we have nearly 2,400 concepts which can be considered as basic. So it's 375, I think, basic concepts. These are dark circles, and nearly 2,000 of red dots. It's those concepts which are considered as basic by their algorithm. So in this case, it's nearly 20% of all concepts, and it's really a lot. So what we propose to do, we say that, okay, the concept can be considered as basic if it has a very nice distribution, which can be easily and very nicely fitted by some continuous function. But this can happen for basic concepts, true basic concepts, but also this can happen for those concepts which are popular at the moment. For example, a lot of papers start to address some problem, and these concepts, these words are used more frequently, so the entropy of this concept will grow. And we show that if the entropy grow for a certain concept, the residual entropy will decrease. So we have these examples of energy conservation and mass. These two concepts, we can see how they, what is the dynamics of the Shannon entropy and residual entropy for these two concepts. And we say that, okay, if we have the time series for all of these concepts which were taken as basic by their algorithm, we can.
May I put a question here?
Yes.
So these two plots you show us, left-hand side and right-hand side, are they different or are they similar? What should we learn from these plots? Could you comment?
So first plot, it's time series profile for Shannon entropy about the energy conservation concept. Yeah, it's we can calculate for each period of time the entropy. Yeah, so we have a certain distribution which changes during.
No, it was not my question. I believe we understood what you plot here, but my understanding is that both concepts are basic concepts. Or you want to convince us that one of them is basic, another one is not basic, or what's the goal?
Yes, I want to say that, for example, for energy conservation, it looks like basic, but you can see by the values of the entropy here, it's really not very high. So the scale here and scale here for mass, it's absolutely different. And you can see that here for a mass we have a difference from 3.4 to 4.2. So it's not really big interval of values for Shannon entropy. It's nearly continually very high. Yeah, but for certain concepts, could be a situation that entropy goes up and the residual entropy is really low, and this concept will be considered as basic.
Well, then this depends just on definition. In my private definition, energy conservation is a basic concept of physics. But if by basic concept you mean something different here, then maybe.
We are taking only some statistical data that we get from particular literature. So energy conservation is really very basic term in physics. It's absolutely more than basic. So everything is obey the energy conservation. But as consider the term which is used in the literature for particular problems, regardless of high energy physics or something, it's not that frequently used as mass.
Okay, thank you.
Yeah. And we want to say the following thing, that some of the concepts at particular moment could be started to very frequently used in the literature. Then we will have a very low values of residual entropy, and by mistake we can put these concepts as basic ones for this set of papers or set of documents that we study. So what we propose, we say that, okay, we calculate the time series of the entropy for each concept which were considered as basic by science-wise algorithm, and say, let us find distances between the time series of these concepts. This will say how they are used for long period of time. So two basic concepts, they are frequently used at any point of time in 1992 and so on and so on and so on, up to 2018. Yeah? But some of them can be different. So what we did, we calculate the time series distance matrix using warping distance between time series, and use a multidimensional scaling to put them to map them on 2D. And we can see that, for example, those concepts as energy, mass, and field, measurement, particles, potentials, which are can be considered for this particular literature that we are studying true basic concepts. You can find it nearly in any paper. We used these scaling to make some scoring of these concepts. In order to say that this line is okay, we put a third dimension in some sense and say that okay, we find that mass, energy, and field is really very basic concepts, and some less number of them can be considered as basic. Yeah, this new red dots. It's according to some threshold. Of course, if you will put this threshold down, then we will say that all 2000 concepts which were selected by science-wise algorithm are basic. But this is an additional degree of freedom to say that we can adjust this limit and say that some concepts are basic and some are really not. Maybe they are popular at the moment, but they are not basic. So that's our proposal to manage this problem of basic concepts. And we later use it to define some seed concepts for topic detection. So the next step, what we did, we determined the distance between two concepts using the mutual entropy. So the formulas are here. We find that this would be a normalized distance, and concepts absolutely unrelated concepts would have on a distance 1 from each other, on a unit distance, and those who are would be found always together in any document will have a 0 distance between each other. So it's really 2 gram. Yeah. What we did then, we want to calculate exactly the distance matrix out of group of concepts. Of course, to select, to calculate this distance matrix among 16,000 of concepts, it's really difficult for a computer to calculate. We are trying to improve this problem because this matrix is really interesting to analyze, but we developed some technique to extract some topics, or at least a group of concepts that can be a source of a topic. What we did here, we say that in our case, we want to build some iteration procedure to calculate group of concepts, to extract a group of concepts. We take some arbitrary seed concept. How we take it, it's a different issue. It's a lot of different methods how to select, for example, good seed concept, but we can really take arbitrary. Then what we did, we find all the concepts, all the documents that mention this seed concept. After that, find all the concepts that are mentioned in these documents, and took only 10%, only those concepts which are appeared in 10% of the selected papers. They would be most close to this seed concept. Typically, we have then a distance matrix for 800 or 600 concepts. We analyze this matrix in some sense that we have here the example of such matrix for a gravitational wave, and say that each position here in this matrix, each matrix element, it reflects the distance between two different concepts. And if it's close to 0, then these concepts are really very, very close to each other. And the red matrix elements, which you mentioned here, it's close to 1. I think my color scale is missing. Okay. So the red color is distance near to 1, and the green color is really 0. Yeah, you can see it's a diagonal matrix. What we did, we sum all the matrix element in a row and score all these concepts according to this number, and say that the smallest number will correspond to a concept which is most connected to all this group. We took this concept as a next step for iteration as a seed concept. Work with it. And after that, going to this dense area of concepts, we select a closely related group of concepts, which we say that could be a good start for topic detection. It's so to say that it would be, we need it later on, that we see here. Okay, that I already explained. So we can say that it's the following thing, that this group of concepts that we have here, they appeared in some hypersphere where the largest distance between concepts is it's not a diameter, it's a multidimensional object. Yeah, but we have, for example, the largest distance is definitely less than 1. And all of them are sitting in this multidimensional hypersphere inside. So what we can do to study the structure of obtained group of concepts, we can make certain filtering. Yeah, we can, as an example, we have a picture here. For example, it's a ice, yeah, cubes, but you can imagine some mountain valley which is filled with water. In some sense, we put some threshold parameter, and we cancel those connections which become greater this threshold. So in some can imagine that we have a full graph, a complete graph, yeah, and we cut some lines inside which are weak links between concepts. In this case, when we did so, we can apply usual methods for clustering of a graph. So example of the graph you can find here. For example, it's for neutrino oscillations for a certain threshold. Yeah, not very high, because in this case, all these concepts became separate. But for some limit, we can find similar graphs. And after that, we can use clustering algorithms that were explained, for example, in previous talk that were in this seminar on the past year. there was a lot of techniques how to use the clusterizations for such problems. Yeah, and yeah. I will not show these examples here, but it's also a possibility to study the structure. I think it's an interesting point that the internal structure, one of the possibilities to map this internal structure for a group of concepts is a minimum spanning tree algorithm that can be applied for this graph. And we can see, for example, the strongest connections between concepts. It's a kind of a tree, and we can see a group of closely related concepts here, and that could be also say that we can find some subtopics in this general topic that we detect. To explain what is written here, so we have a circles as a concepts, and the color of these concepts is set for derivative of the corresponding entropy time series. For example, we have let's say atmospheric neutrino. Yeah, sorry. Okay, we have atmospheric neutrino, for example, and we calculate the time series of the entropy for this particular concept, and we can find the derivative for past 4 years, starting from 2016, for example, yeah, and end at 2018, yeah, and say that okay, the color will say how the entropy, if it grows or it decays for each concept. The size of these dots, yeah, it reflects the number of documents that mention a particular concept. We have some set of documents, yeah, which mention this one, and we don't look at the term frequencies. We can just count, okay, in this paper this concept were mentioned, then we can count number of papers and to say that the frequency, document frequency, can be mapped as a popularity of this concept also. That's another possibility to map a structure of the concepts. Another one approach is a multidimensional scaling of obtained matrix. We can simply map it on 2D and use the hierarchical-based clustering algorithm to find the subtopics of this matrix. And we can see that by the shape of the points, this clustering algorithm show us the subtopics. It's you can see that in this case here it's more experimental concepts. In here we have more theoretical concepts which were separated by this algorithm. Before up to now, we discussed here the static structure of concepts, and you can find many examples of this in the literature. But the interesting point and how to find the dynamics of these structures and to extract some useful information out of there. Many approaches are based mostly on the mapping. So we, for example, get this map of concepts and then trying to propagate it in time. But there were some big mathematical difficulties, for example, like alignment problem, because the multidimensional scaling of such a matrix will show always a similar picture, but to define which concept you are working with and how to put the line between them, yeah, it's a difficult problem. We propose to go one step above, to say that okay, we have a very nice matrix, it's a symmetrical, it's a base triangle inequality, and it's a good point that it's actually a geometrical object. We can say that it's really a simplex, because, for example, if we have all the disconnected concepts, they all set on a distance of unit from each other. It's really multi-dimensional simplex. The simplest two-dimensional simplex is just a triangle, yeah, with a unit distance between the points. And if you go for higher dimensions, we can include a lot of concepts there and say, okay, let's calculate the volume of this simplex, the unit simplex, and deformed simplex. Because deformation of simplex, when it's shrinking, it shows that some discussion is going on, and these concepts are connected. And the smaller volume occupied by the concepts, the more active discussion is going on with this group of concepts. So what we did here, we we calculate the distance matrix between 35 concepts here, yeah, which have at most distance from each other is 0.96, and then calculate the volume of unitary simplex of 35 dimension, 36, yeah, because it's different. And then we have this deformed simplex. We have V over V unitary, and to calculate them over time. If you not scale them properly, you will see that these volumes are really different, because we have a different number of concepts when we are shrinking this multidimensional hypersphere. Yeah, and here we say we show the scaled to a unit all these time series, and we can see that, for example, for neutrino oscillations near 2000 or near 2007, yeah, for a particular group of concepts closely related to neutrino oscillations, we have some shrinking of the volume of this simplex. So it can be an indication of active discussion which going on for a certain group of concepts, physical concepts. And the good thing that here we don't need any mapping. We are using just geometrical interpretation of our distance matrix, and very easily can trace its dynamic over time. In this case, we of course have some only part of information. We can trace only a certain number of concepts which are initially at 2018 in some hypersphere of this with this d max, yeah, diameter, but we don't know, for example, what is happening at the beginning here, because maybe these 35 or 23 concepts were unrelated absolutely at this point, and these dynamics that we have here, it's just a simple fact that they start to mention together, and the corresponding simplex start to be smaller. So what we try to do next, we say, okay, let us look at this situation more closely. For example, at the beginning of our time series, it's 992, we calculate the distance matrix out of time series, out of the data that we have, what concepts would be in this hypersphere at the beginning, yeah, at 1992 of our data set. And we can see that not very much of concepts are sitting here. It's only 6 of them, yeah, appeared in this hypersphere. But at the end, at 2018, we have a very we have a lot of concepts which are associated with these neutrino oscillations concepts. We decide to see how these concepts are entering in these hyperspheres, to say that for 1 year, for example, what is changed, what concepts are entering in a smaller of hypersphere, a smaller diameter, or maybe leave this hypersphere. So in this case, we say that, for example, from 1995 to 1996, for example, I think this data that 4 concepts changed their positions, and that means that they change all the relative positions inside of this actually 7 of concepts. And that also can be an indication of a hot topic, because if they simultaneously change all these distances between existing topic, it means that all of them were intensively used to discuss some problem. And that's one of the approaches that we propose to say that how to detect hot topics within this framework. And we can trace all these dynamics for all years, how these positions of the concepts are changing. And to say that, for example, here we have a lot of concepts, but still active discussion is going on, and concepts still changing their position to a smaller hypersphere, entering the more dense areas of a topic. And here, for example, these are good seed concepts to calculate some group of concepts to find the hot topics. It's one of the approaches. And one more that we propose here is actually based on some physics things. To say that we can calculate the distance matrix for two subsequent intervals of time, for example, for 2017 and 2018. And then we can find the difference between these distance matrices. That would be a velocity, that will be a speed, how these concepts change their position. Of course, these are relative velocity. Some of them are going apart, so that would be positive or negative velocities. So what we did here, we say we can calculate such a velocity matrix, and using the spanning tree algorithm to detect those concepts that gets closer to each other. And we find such interesting stars of concepts which are getting closer for past year. So it's just 1 year information. So for example, for this 2018 and up to 2017 to 2018, certain concepts are getting closer, actively getting closer, and we may find these groups of concepts. And each of these star can be considered as a hot topic because we have the fastest concepts which changes their information, their positions a lot. These are all methods that we propose here, and probably I will say something about the possible future method that we are planning to incorporate in our research. We have, for example, a possibility to use transfer entropy to study information transfer between adjusted time layers. It's similar to mutual entropy, but this is a mutual entropy between two time slices. This approach is mostly used for brain search. It's some biology method that is used there for to study perception or information flows in a human brain or similar complex networks. It's easily to adopt our methods for this transfer entropy. We also can say that it is very challenging and interesting. We already did that, but we still need more research how to introduce another thermodynamic parameters here, for example, energy, temperature, and others to build some thermodynamic relations between concepts. We have a velocity, we have entropy. Energy is also a possibility to introduce there in temperature. There is good methods to introduce it to say how which concepts are really hot in the sense of a temperature. We also planning to use the forecasting methods to say what will be the future values of entropy time series. Using some quantum Monte Carlo or path integral forecasting approach, there are interesting methods to do that.
Okay.
Yeah.
May I ask a question?
Yes, of course.
This is Michael Emmerich from Finland. I'm interested in this hot. What do you mean by hot? Is it just a high frequency of mentioning, or is it something more profound?
No, it depends on how we introduce the temperature. There is a possibility to introduce it based on distribution of term frequencies. So we are fitting a distribution with a certain function. If it's 2-parametric or 3-parametric, it doesn't matter. Then there is a methods which discussed in information science how to say that for such a distribution we have corresponding definition of a temperature.
Okay.
And, yeah, having this temperature, we can scale it. We can calculate this temperature over time, and to say when this concept became hotter or colder. And that would correspond, of course, to the velocities. Of course, if we have some concepts which changes their position a lot, then corresponding temperature will be high.
Okay.
Yeah, and
So
it's very interesting to build such a thermodynamics, really thermodynamics of concepts in this respect. So another problem that is actually where initially in the project of ScienceWise, it's a construction of it's multimedia, no, multi-networks, sorry, there's a mistake, of concepts, articles, and authors. So our measure can be easily adapted to calculate the distances between not only concepts, but between articles or authors. And when we have such a 3 networks, we can easily find the connections between them. It's, of course, the open questions. There's a lot of details, but this network can be very interesting to trace the hot topics and hot author communities, or some very hot papers which are statistically defined within this group. And combining this with the forecasting methods, we can possibly find some new things out of this. And another direction of research that we're discussing here is machine learning methods to find the future active research topics. Also, but the most interesting is think how we can, for example, for a certain hot topic, to make machine learning algorithm to write a new paper out of it. There is some possibilities. There is some algorithms which already show their good quality in text construction, in some very, how to say, meaningful text constructions. And if we have, for example, a big set of concepts which are related to hot topic and topic, we can ask this algorithm to build and to write something new, combining these topics. Maybe that would be an interesting thing to learn what would be there. So that's all. Thank you for your attention. I hope that was useful and interesting for you.
Thank you very much for such for very nice talk, full of information, full of details. I'm sure we will have a lot of questions. So please.
Yeah.
May I start then, if everybody else is thinking? Honestly, it was too informative for me to catch everything during the seminar, but some questions appeared. For example, the very naive question. Okay, so using your methods, you were able, let's say, to see some structure of topics, etc. Was that somehow verified by experts, somehow by different methods? Why you're sure that? So how we can be sure that this method is really good? I mean. Usually after the application of some automatic methods, experts, human can verify this.
Yeah.
So,
thank you for your question. Yes, of course. Why we choose this high energy physics and exactly the neutrino oscillations concepts and some others. There is a specialist, for example, Boyarsky himself, or Stanislav Josip-Wilczynski, and others to whom we talk. We show these pictures, and it's they said that this is can be true, yeah, in some sense, because a lot of concepts are connected correctly. Of course, there is some something that they say, okay, this is missing, and that I would say that these are concepts more closely related than others. But so to say that we are personal opinion is always based on a long interval of time. It's a full opinion that we have about the subject. But now we are discussing and looking only at the particular slices of time to find the connections. Yeah, experts were positive about that.
okay.
Not 100%, of course. Yeah, they said that, okay, we think that this could be maybe different, but I think 95 or something like that, they were positive.
Okay, thank you. And another question is, well, as I understood, you took only keywords provided by authors themselves.
No, it's not.
No?
No, it's not correct, because it's not the keywords provided by authors. It's the keywords which were collected by the ScienceWise from the all papers that they have. So some scientists can propose their keywords, their concepts of physics, which may be not even used in the papers. They say, okay, these two words means something like that. So it's a separate thing. We didn't take just keywords that author say that these are keywords for this particular paper. So for a certain paper, we have maybe 500 or 100, from 100 to 500 concepts in a single paper.
Okay, but anyway, you had the set of candidates, a set of concepts in your hands. Is it possible to use somehow these methods vice versa to detect important terms or concepts having full text and no hints, no preliminary knowledge, just when you have the bag of texts, corpus? Is it possible to use some of your methods to say that this word is important, this word is concept or not?
That's an interesting question. I think it's addressed to the question of how concepts actually, how to say, be born. Yeah, maybe it's народжуються. Yeah? So how they get to life. Yes, and that's interesting approach that we also look at, but not yet fully work with, because, for example, we can see that in our database some of the concepts didn't mention before. For example, gravitational wave or black hole or something like this. Up to a certain period of time, there is no literature which mentioned these words, and then they appeared. And we have actually a lot of concepts that appeared during the year. So it's 3 or 4 or 5 of them. So if we take all the data of how new concepts enter this ontology, when they enter, which are the relations, and what are the main principles, how they appeared. So we have a structure, we have knowledge that a certain concept appeared at a particular moment of time. It was related to this concept, and then you can see the dynamics of this group, and to find that how these dynamics maybe influence the appearance of this new concept. And that could be a possibility for future prediction of new concepts as a combination of old one or something new.
Okay, but I thought that maybe if we can take all the words, just all the words, to use all these methods to calculate all these things, and maybe it will be possible just having raw data, raw text to define candidates for concepts automatically.
That's. I think these algorithms are developed in ScienceWise. They make it. They doing it. There is some kind of Profi Science. They build a new web-based algorithm where they continuously detecting new topics and new keywords.
I see. Okay, thank you.
Yeah, so they have this algorithm. We didn't develop it ourselves. Yeah, but it exists.
Thank you.
You're welcome.
May I ask a question?
Yes, please, Reinhard.
My name is Reinhard Volk. I'm from Linz, Austria. At the end of your talk, you said you want to find out, so to say, by an algorithm in some way, future hot topics.
Yes.
And so this is something, you have some algorithm and you can predict something. Couldn't you use this algorithm on topics which were already which arose in history? So, for instance, you want to understand ferromagnetism. And how could one understand ferromagnetism? Could we do this without the concept of spin? And can you find out that the concept of spin could make this topic hot? And could you also find that a hot topic is also a topic which has an increased number of papers appearing in the journals?
Yeah, I think it's a good question. Thank you for this. It's closely related to the previous question, of more new concepts. Yeah, we can say that what we already saw in our calculations, for example, let's see about maybe time series. No, it's better to see what over here when we are discussing some simplex. Actually. What we found that these shrinking of a volume of a simplex is usually predefines the growth in the entropy in some concepts. So, for example, we have a shrinking of the volume, and after that, certain concepts are fire up. Yeah, they have a very high entropies start to grow. So this mechanism is very similar to that. We can trace when the simplex volume is shrinking, and to say that here there's the point that new concepts may be born, or some of the existing concepts gets a new insight and they start to discuss again more. And this could be only some new idea came to understanding. Yes, so that's maybe one of the possibilities to predict that we need something like spin or some another concept to explain that discussion with what's going on. But we are still working on it. There is not yet developed technique that I can show to say that we can predict that, for example, idea of spin will be born.
Okay, thank you.
Yeah, welcome.
We have questions, so please, Mike.
Yeah, thank you. In fact, I have two short questions or comments. The first one is that recently we, together with Vasil Palchikov and with a student from Ukrainian Catholic University, we were interested in a bit similar and also a bit different question. And the database was the same. It was based on archive analysis. And we were looking how do innovations appear. And the zeros hypothesis was that either new concept appears or new link between old concepts appear. Yeah, is a new concept, or some old concepts are linked together, are used together in the same text. Yeah, and I sent in the chat to all of you the link to the preprint on this topic. And the question to Artem is, and of course, many thanks to Artem for this nice presentation. The question is, would it be possible, how do you think, just using your technique, to look for the appearance of new links between old concepts? And could you comment on this? That's the first, and then the second will be very short also. Thank you.
Okay, I think this slide explains how I will answer this question. For example, the problem is that we, for old concepts, already have some links, and they exist, but they can be weak, and they could be stronger, get stronger with time, and we can trace how stronger they became in respect to all the concepts in this group. And exactly new links can be said that these old position and new position, yeah, that we have changed, and this is in some sense we say that a new link is appeared, because we can cut these small links before and say that some concepts appeared outside this hypersphere, and after some time it enters this hypersphere. It means that links get stronger than certain threshold, and this is exactly what you say, that we have a new links in a group of topics, and we can say that this new link may be indication of something new appeared.
Okay, thanks. And another question is, you mentioned that you can introduce temperature by looking on the distribution. You have distribution, and then you say that it is energy divided basically by temperature, and you have temperature. And are you aware about works of Andriy Rovenchak from Lviv, from National University in Lviv? He was measuring the temperature of texts, and he compared different languages and the temperature of texts of the same text when translated to different languages. And I mean, the problem statement for me was very interesting, and also an outcome of analysis was very interesting. Are you aware about his contribution?
Not yet.
So in chat,
yes, but I didn't get there.
Yeah, even in Ukrainian, the title of his paper is very nice because it is Temperatura и literatura. So, you know, as a poem. Send you a link in the chat, just personally to you. It is a link to his paper. Thank you.
Thank you. That would be very interesting. Yes, indeed.
Thank you. Yes, please, we have another question.
Okay. It's a question about the prediction of trends in science. Subject of computer science often discussed is the Gartner hype cycle. Have you heard about this hype cycle of Gartner?
Very, how to say, very briefly. I have time to look at it more closely.
It is very often shown in presentations to motivate that some concept might become very important in the future. But from my point of view, it might be interesting to understand better the mechanism of such empirically found hype cycles of trends in science. So perhaps this physical model can shed some light on the mechanics.
Okay, thank you. I will look at this. I will look at that. Maybe we can say something about this cycle from the physics point of view, that from that what we have.
Yes, I think that would be interesting in terms of prediction of trends and typical waves that occur.
Okay, thank you.
That was a comment.
Thank you.
Thank you. Do we have more questions? I have just a suggestion, maybe, or a comment. You mentioned that you plan also to build multi-layer networks to take into account the information about authors, and yes, on a paper level of authors, etc. And it came to my mind that maybe you know this paper in Nature about so-called disruptive index. It is calculated using some citation data, but it tells how it characterizes the research results as like some hot topic, something very important, very hot, is characterized by high this disrupting index. And the authors in this paper in Nature, they found the correlation between the size of research groups and this disruptness index. So they say that small groups are the potential to find something really new, really hot is higher for smaller groups, and that larger groups, they usually do some research, like developing research, if we can say so. So not so disruptive.
I see.
And I think that maybe when you will have this author data, different levels, maybe you should look at the size of groups, of research groups, and to see, to try to see, to find some correlation between this hotness of new topics and the size of the collaboration co-authorship teams of the corresponding papers. So that was just
Okay.
the idea.
Thank you. Yes, that would be interesting to see. Yes, I aware of a fitness index which was introduced. Also, there is a papers in the Nature, but this disruptive index I need to look at. Yes. Okay. Thank you.
If we have no more questions, I suggest to thank our speaker again. It was very interesting, and yes, using this opportunity, yes, we would like to suggest everybody who are interested in scientometrics and physics altogether in complex systems we invite you to participate in our seminars, and maybe we should organize more scientometrically oriented seminars. We are very interested in that. So we would like to communicate and to discuss more.
Yes, definitely. Thank you. Thank you again for this opportunity. Thank you for your attention. I hope it was useful.
Thank you very much.
Thank you.
Goodbye. Thank you.
Thank you. Bye.
Thank you. Goodbye.
Thank you. Bye.
Артем,
Так, я тут ще.
Поки ви ще тут, можна ще дещо так якби в кулуарах?
Можна, звичайно.
Я стосовно, ви там згадували такі густі мережі, що коли є дуже, ну якби багато, майже повні мережі, і що ви застосовували, ну так якби використовували спрощення мережі. Тобто відсікає оці острови, що ви говорили, то ви відсікали по товщині лінку, використовуючи певний поріг, просто відсікали слабкі зв'язки. Це я правильно зрозуміла? Чи це був якийсь більш складний алгоритм?
Ні, насправді алгоритм дуже простий. Ви маєте матрицю з матричних елементів, і ви просто віднімаєте від усіх матриць певні значення, так, і дивитесь, чи це значення, яке ви отримаєте, буде більше за певний поріг або менше.
Ну, тобто, фактично, ми встановлюємо критичне значення товщини лінку і тонкі ігноруємо, так?
Ну, так. Тобто ви берете, кажете, що якщо цей лінк близький до одинички, то давайте ми його поставимо дійсно одиничкою. І тоді, коли він буде одиничка, це буде в нашому алгоритмі означати, що це абсолютно не взаємодіючі параметри. І після того ми можемо дивитися, навіть слідкувати, чи з'явиться цей лінк в майбутньому. Тобто ми можемо аналізувати цю матрицю в часі і дивитися, чи з'явиться цей лінк в майбутньому. І це якраз цей link prediction. Тобто це, можливо, якраз один із методів його знаходження, таких от нових лінків.
Ага, просто сам термін, оцей islands, він мені нагадав, я бачу, ну, є такий, читала підхід до, власне, теж спрощення, редукування мережі, а він ґрунтується не просто на, ну, якби на встановленні якогось критичного значення чи там відкидання слабких, а от я зараз розшарю свій екран, це буквально з лекцій, які ми в УКУ готували, і там є зараз, просто хочу вам показати, може згодиться, зараз, секундочку. Бачите мій слайд?